So in this video, we're going to look at changes of state. So we've already talked about how the three states of matter we're interested in, solid, liquid, and gas, and how the kinetic, we've already talked about those, and we also how the kinetic and potential energies increase as we move through these states, so from solid to liquid and then to gas. We also know how much energy we need to put into heat a substance to a certain temperature. We learned that through looking at specific capacity. But what happens as we transition from one state to another state? So we start here with ice, and then move on to liquid. Our specific capacity has told us how much it takes to raise, a particular state of matter. So from water, it tells us how much energy we need to raise water from 10 degrees to 20 degrees or something. But does it just work over the boundary? And the answer is, well, no, actually, there's going to be a different specific capacity for water as ice than for water as liquid water. And also, it doesn't just work straight across the boundary. There's something more important going on here called a phase transition, or a change of state. And there's different energy transfers going on here that we need to be aware of. So we can see that by plotting a graph of temperature against time as we heat a substance, which I've done below. So we start here at it just, at our solids. Then we decide to start applying heat. And we're applying it at a constant rate, which really means that this time is the same as just energy needed, right? Because if we're heating at a constant power of P, then our work done at any point is just P times the time, and so we can see that really this could just be energy as well. It would just be the scale would be different, but it would be the same as this is just also like increasing energy, increasing total energy, but the power remains the same. The energy per second is the same. So this is increasing the total energy of the substance, but power is constant, which means the total energy transfer per second is constant. So we can see that the longer we spend at a particular state, the more, first of all, sharper here, the fact that this is steeper, means that we get more of a temperature rise for each extra bit of energy we put in. The temperature rises more, which might be the case or might not be the case depending on the different substance we're talking about. It might be that it raises its temperature more easily at a liquid than it does at a solid, or it might be the other way around. It just depends on the properties of the object we're talking about. What we do find is that we start here at our solid, and we apply some heat, then we get to the melting point, and then we stay there for a while. So we're still increasing temperature, we're still increasing energy, so we're adding energy here, because the power is remaining the same. But then eventually, but the temperature is constant. And then what we find is that we start to, our temperature rises again. So our temperature is going up and the total energy. From now on, whenever I write energy in this little bit here, just when I'm talking about this graph, I'm going to mean the total energy. It's not that we're increasing the rate of supply of energy, that's constant.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.